Raise the roof, roof, roof.
After getting done with the introduction to Newton's second law, I decided I should probably have a part 2. All right. There's a couple things I want to cover in part 2 here. One is the units associated with Newton's second law, and also what happens with Newton's second law when you're actually on an incline. I know in the first part for the introduction to Newton's second law, I talked about a box being on some wheels, okay, on a flat surface, and finding the net force. But what if that object happened to be on an incline? What would you do? All right, so that's what we're going to do in part 2. So our equation, F equals ma, all right, has force, mass, and acceleration. Okay. The SI units associated with those 3 variables are the Newton, the kilogram, and meters per second squared. So the Newton goes with force, the mass goes with the kilogram, and acceleration is meters per second squared. Okay? So we can write that as 1 Newton then equals 1 kilogram meter per second squared. And this is very important because when you do the problems, you want to make sure units cancel out appropriately and correctly. You need to know that the Newton is a kilogram meter per second squared. Okay? I also want to compare that to another equation, weight equals mass times gravity. Okay? And that's something you may have seen before, and I may have mentioned in the part 1, but I'm not exactly sure. Can't remember if I did or if I didn't. And if you were to actually pair these up, F equals ma and W equals mg, it is the same equation. Weight is a force, mass is mass, and we have the acceleration due to gravity, which is an acceleration. So the units for weight, mass, and gravity line up exactly with our newtons equaling kilogram meter per second squared. Okay. So there's the SI units. The next thing I want to talk about is an incline. A little extra big for you. Okay. Now how about if I were to put a box on that incline? You could still put it on wheels, just like the first part. We know that this box has a mass, okay? And that if it has a mass, it's going to have a weight here on Earth. We would call that W. Now the thing about Newton's second law is that when you're trying to find accelerations and stuff of objects, we care about the force and the direction of motion. So what is going to cause this to actually roll down the incline? Most students and most people would probably say, well, the weight's causing it to go down the incline. And that's somewhat true, but not exactly. Okay? So let's break this down. Let's break the weight down into 2 different components. Okay? The one we'll call Wy, and I'll explain here in a second or 2 why we have this lined up the way we do. Wy. Okay? And then we also have what I like to call Wx. And I'll also explain why I call it y and x. Wx here. Now this might look a little funny, but this is a right triangle. Okay? And we also know that if we have the angle of the incline, that is also equal to the angle made by Wy and W. The reason I draw the vectors the way I do, Wy and Wx, make sure vector sign there. The reason I draw those the way I do is because Wx is actually pointing down the incline. So if you were to be asked the question, what is actually causing the object to go down the incline, you should probably be specific and say Wx. Now remember, we could actually draw vectors anywhere we want, okay? As long as it's the same direction and the same size, it is the same vector. So Wx on top right here and Wx right here are the same. The reason that I draw the triangle the way I do is so that we can just use the same angle and not have to play with the angles at all. Okay, so how would I find Wx? Well, we have a right triangle, and if you notice, Wx is now opposite the angle. Wx, or the x components in projectiles, were always adjacent. Now we have to be a little bit particular about what we do. So let's go ahead and solve for Wx then. Wx would be sine, okay? So it'd be W sine of theta. If we needed Wy for some reason, we would solve Wy is equal to W cosine of theta. Okay? So this gives us a little breakdown of vectors. And it also tells us that Wx is what we should use when we're trying to do force problems on an incline, at least for now. So now let's think about what would we call positive and what would we call negative then. In our typical x and y axes, positive x points to the right and positive y points up. Okay? So that would leave W being a negative value. For example, the weight would be negative 100 newtons, meaning it's going down. But now we actually have some components in some other directions. Okay? So if you're sitting there watching this, you can make an L with your left hand, your pointer finger, and your thumb, and you can tilt it from y being straight up to now y being at a little bit of an angle, and that would actually give us a new axis where positive y is pointing up away from the incline and positive x, let me see if I can draw this, positive x is actually pointing down the incline. Now some books and some other people might do it a little bit differently, but I like my positive x pointing down the incline, and the reason I like that is because then you have positive accelerations and positive forces, okay? And also the positive y pointing up away from the incline will also be nice when we do friction, okay? And I'll just leave that the way it is, okay? So once you use the weight to find the components, just like in projectiles, you're not going to use it again, okay? We set up a new axis system, all right? And we solve for Wx and Wy along those lines. Okay? Now the last thing that I'm going to mention here is an object being on a flat surface again. And it's sometimes something I just overlook and I don't think about. But let's say we have an object on a flat surface, okay? And instead of the force being pointing like directly to the right or directly to the left, let's say it's at some sort of angle. And we'll call that theta. Now if you were to pull on this box and there's no friction, okay, the motion would be to the right. Okay? Now there's a slight possibility, depending on how hard you pull, that the box will actually lift in the air. But in this case, let's say it's not. So it's slid along the ground and it's pulling right to the right. Well, we can't use the whole force here. Okay? Just like the incline where we use Wx, we have to use the force in the x direction. We call that Fx. All right, so if we were to solve for the acceleration of this, we would say F equals ma, and to be more specific, it'd actually be F equals mx, Fx equals m times ax, because we only care about the x direction. All right. So how would I solve for the Fx, okay, if I just had F? Well, now once again, I would have my right triangle here. Fx is going to be adjacent to theta, or the angle. And so fx would also be equal to f cosine of theta. Okay. Okay, so that's the end of the second part for the introduction to Newton's second law. We talked about the units. We talked about angles referring to an incline, and also angles on a flat surface. All right. In the example problems that we're going to do, that I'm going to do and I'm going to put up here, and even ones in class, they're going to involve these three things. All right. Angles on a flat surface, objects on a flat surface, objects being pulled at an angle, and then objects also on an incline moving down the incline.